Very good evening to all of y'all. Today we'll be covering the topic of binary search tree. We'll be solving certain number of questions. So the knowledge that's required to attend today's session is we'll be looking at the various tree traversal techniques. That is the Inorder technique, the Preorder technique, right? So let me quickly recapitulate it, the ones which we have already covered in during our DSA sessions. So let me just reiterate all of those concepts, and then we'll quickly start off with the problem solving. All right. So assume that we have a tree. A tree consists of nodes. So it has a root node, and then it is further divided into branches, and they have leaf nodes. And the end of the tree is always at a leaf node. Okay. So now let us assume that we have a tree here. With these particular nodes. All right, so I have a root node as 1, then I am having another node as 2, which is further divided into 4, and the right side has another node 5, and then root 1 is further divided on my right side to 3, and then I am having 6 on the right side. All right. Assume this is a tree that I'm having. Now, I told you the knowledge that we require for this session is the various tree traversal techniques. So let's first discuss the in-order traversal technique. So what happens in in-order technique is the first thing that the pattern that the tree follows is we come across the left node first, okay? Then the root node is read, and then we move to the right node. This is the way that a tree is either constructed in our in-order traversal technique, or even printed, or the elements are read in this order when we are talking about in-order traversal technique. We first accomplish the left side of the tree, the left node, then we speak about the root node, then we move on to the right node. So if we are talking about the in-order traversal at root node 2, then the first thing is node 4, that is on the left side. Then we cover up the root, that is 2, and then we have the right side of the node, that is 5. So this is the technique. We first visit the left side, then we move on to visiting the root, and then we move on to visiting the right node. Okay, so we start off with the left, then the root, and then the right. This is your in-order tree traversal technique. All right, so moving on to the next technique that we have. So the next technique that we have, tree traversal technique we are going to talk about, is your pre-order tree traversal technique. So when we are talking about the pre-order, we are first going to visit the root. Okay, then move on to the left node. After visiting the root, we move on to the left node. After visiting the left node, we move on to the right node. All right, this is the order of a tree traversal technique, that is pre-order. Pre-order, and this is the technique for in order. Okay, so in pre-order, what do? We first read or come to our node, root node, that is 1. Then we move to the left node, the node that falls on its left, that is 2 here. And then we parse or read the right node, that is root node number 3 here. Okay, so this is our pre-order traversal. In-order traversal is we start off with the left node, then move on to the root node, then we move to the right node. This is the order in which the nodes are read. Okay, so these are the two traversal techniques that we will be utilizing in today's session. Along with this, we are going to come across something called as the binary search tree. Now, what is a binary search tree? A tree in which all the values on the left side of the node are lesser than the node. It is mandatory that all the values that fall on the left side of our root node should be less than the root node. And all the values that fall on the right of the root node have to be greater than the root node. Okay. For example, if we have 9 as our root node, then all the values on our left are going to be smaller than 9. Okay, so we can have 6. Fine, smaller than 9. Then the next one we can have 5, smaller than 6 and 9, correct? And then value on the right can be value 7. So that is greater than 6 because it's on the right, but smaller than 9. Then 5 can further be divided into 2. Okay, we have reached the leaf node, I can say. I'm stopping this here. And then on the right hand side, we are going to have all larger values. So here I can have 11. Then I can have 10 here. It's greater than 9, but lesser than 11 because it's on the left side. And then here I can have a value 14, greater than 11 and greater than 9. So what's happened here? All the values of the root node on the left hand side, that is this side, are lesser than the root node. And all the values on the right hand side, that is this side, are all greater than 9. So the values in a binary search tree, the root value needs to be greater than all its nodes on the left side and should be less than all the values on its right hand side. When this condition is approved, it is known to be a BST, that is binary search tree. Okay, two conditions: all the values on the left hand side should be lower than the root node, all the values on the right hand side should be higher than the root node. Simple. Okay, that's called as your binary search tree. So during this session, please remember these topics. We are going to be moving back and forth with this, the tree traversal techniques, and also your binary search tree. All right. So with this knowledge, let's start off with the session. So the very first question that we are coming across here is, given the root of a binary tree. So the root of the binary tree is already given to us. We need to return the in-order traversal. A list is given to us, a list of numbers is given to us, and a root is given to us. So we are going to return the in-order traversal technique. What are we going to do in in-order traversal? What did I tell you about in-order? We are going to first start off with the left node, move to the root node, then the right node. This is the order in which the tree is going to be traversed or the tree is going to be visited. This is the order of the nodes. So now let us make sure that the tree is visited in this order only, because we have to return it in order traversal itself. Okay, so the very first thing that we are going to define is what is the structure or what is the nature of the pointers that we are going to be pointing or utilizing. For these nodes, we have to utilize pointers. So we are going to be first defining the pointers. So let me define the class called as tree node so that we can define the nature of it, like how many pointers do we require, what values we are assigning to it, etc. Right? Under this class, I am defining your function, which is going to help us in taking care of our pointers, right? I am creating self, and then value is being assigned. Value, I'm initializing it to 0. Then I'm creating a left pointer. So nothing is assigned to this left pointer yet. So I'm giving it as none. Then I'm starting right pointer. Nothing is assigned to it. So I'm giving none again. All right, this is my initialization. The definition is ready. Now let us mention self.val. This is just giving a structure to our pointers, right? So self.val is going to contain our value. Then self.left is going to contain the left pointer. Then the self.right is going to contain the right pointer. All right, so this is a structure of our pointers. Nothing's been initialized yet. Only when a value gets assigned to it, it initializes. Here we are just telling what particular structure or format we want your pointers in. Okay, what is the data type kind of thing, right? So now let us define your in-order traversal. So in order traversal. So we are creating the traversal technique here, how the nodes are going to be read, in what order they are going to be visited. That's what we are defining here. We are starting off with the root node. They have already told us they are going to give us the root node. Now, if your root is none, this is our base case because we are going to be using recursion here. So if your root node ends up to be empty, so before we start with that, define in order traversal, we are passing the root. Let's start off with a list where the result of the in order traversal will be stored, right? So result is equal to I am starting a blank list. Fine. Now let me define my in order technique. So define in order. In this, I will pass a node. Once it comes across a node, it's going to run this function. First thing is we need to check if the current node is having some value or not. Okay. So if there is some node present, then what we are going to do? In order. We are going to call our function in order. So this is a recursive function. What is a recursive function? We can call, we do not know how many number of times it's going to get called. So a recursive function is a function that calls itself until the loop becomes none or until it becomes zero, right? So now we are calling our function in order, and whatever node we have come across, we are going to assign it to the left subtree. Okay, so the first value that we come across is going to move on the left subtree. Why? Because the order is left, root, and right. This is the order in which it's going to visit. So the very first node number that we come across, we are assigning it to the left. The next, we are going to utilize your result, and to this we are going to add or update your node value. So what is this node value? This node value is the current node that you are visiting. Then again, in order, we are going to move it to your right. Node dot right. So what is this node dot value? In short, this becomes your root also. So that gets appended and node dot value is added. Okay. Next, now let's start the recursion with our root node. So whatever value we have in order, then that becomes our root. Okay. So after this, let's return the result. What are we going to do? Finally, return the result. What does result contain? Result contains the order of node visitation for our in-order tree traversal technique. Okay, so first let me declare the root as my tree node. Okay, I'm giving the tree node as 1, that is the root. Then I am assigning my value to the right. So root dot right, I am assigning it as tree node 2. And then my left, I'm going to take root dot right dot left. And tree node is going to be assigned to 3. Okay, so now what is my in order traversal technique? I'm asking it to print it for me. Print in order traversal. And what am I going to do? I'm calling a root. I'm calling this tree node. So what is my order here? So when I print it, it's going to give me the order as 1, 2, 1, 3, and 2. That means my node on the left, is going to be 1. Then my node on my root node is going to be 3. and my right node is going to be 2. This is how my tree is created. Why is it giving 1, 3, and 2? That's the order in which it's visiting the nodes. First, left node, then the root node, and then it's visiting the right node. This is the order. All right, perfect. I hope that you have understood the in-order traversal technique. Um, Now we are going to move to the next part, that is return the maximum depth of a binary tree. So what do you mean by maximum depth? Maximum depth is how many ever leaf nodes we are accomplishing, how many subtrees we are getting in that, right? It needs to return back the maximum depth of it, or the maximum number of nodes from your root node till the last leaf node, either on the left side or on the right side. So whichever is the highest. If it's highest on the left side, that's the maximum depth. If it is maximum, if a larger number of subtrees are present on the right side, that is the maximum. Okay, so that way we are going to look at the number of nodes that is starting off from your root node till the last leaf node. We have to count it. Okay, so we need to figure out the maximum depth or the maximum number of nodes until the last node in your tree. So for that, what are we going to do? Simple thing, we are again going to be using recursion here. We will declare a function, and that function is going to call itself until it becomes 0, until the value in it becomes 0. Either the left tree or the right tree, the value becomes 0. Until then, it will keep calling itself, and once it's reached right on top, it will stop the execution. That is, it will start its execution from your depth of the tree, and it will keep returning it back until it reaches the node, and then we will get to know the maximum level of your tree. Okay, how many levels? For like how we have various floors in your building, first floor, second floor, third floor. So in the same way, we have various levels in your tree. So what is the maximum level of your tree or maximum depth of the tree is what we need to figure out. Okay. So for that, again, we are going to be declaring the structure of our program, like what are the pointers that are being utilized. So I will create a class tree node. And in this class, I'm going to put my initialization. So let me initialize. Okay, and self is equal to self. In the self, we are going to create a value is equal to 0. Then we are going to have left, which we are giving it as none, no value. Then right, none, no value. Okay, and after that, we are going to have self dot value is equal to the value itself, whatever we have. Then self dot left. So self dot left is equal to the left pointer, and self dot right is going to be the right pointer. All right, so we have defined the structure. Now these values are going to be initialized only when we come across the numbers or when some number is assigned to these pointers. Okay, so what did I tell you? We need to figure out the maximum level in that tree. So first of all, what do we do? First, we will set a base condition. Base condition, why are we setting it? At what point of time your recursive function needs to stop so that it does not end up running as an infinite loop. We need to define a base condition so that your loop stops at some point of time, right? So let us create a function as max depth, and we are going to pass the root value in it. Then the base condition that we are going to define is if there is no root value. Okay, if the root value ends up to be none, then we are going to return back a value. If not a root, then what do we have? Then the value is basically 0. That is no levels in the tree. There is no root, that means no levels in the tree. So we are going to return a 0 here. The next is, if we have some values on the left, then what we are going to do? So we are calculating the left depth. Okay. So, so in the left depth, the maximum depth that we have, what are we doing? We are calling your function max depth again. So max depth, what will it do? It will move from your root to the left side. What is it doing? Root value it took, and now it's moving to the left side. And whatever is there on the left side, that value is being assigned as your left depth. Okay. So it calculated one count, one tree. One node is present on my left. How many ever nodes are present on the left, right? It counted that and stored it in left depth. Same way, right depth. In right depth, we are again calling max depth, and we are going to have root dot right. Okay, we are moving to the right side of the root, and it will count a node. So after it has counted the right subtree and the left subtree, one value of the right, one value of the left, whatever is available, it counted that. Now when it is returning back the value, okay, when it's returning back the value, what it's going to do is it's going to add 1 to it. Why is it adding 1 to it? So assume you have one node on the left and you have one node on the right. So what is the max? One, you have some node called as 1, and you have another node 3. So max of 1 and 3 is 3. Okay, you have other two nodes there connected to it. So you have two nodes, 3, then 1, 2. Okay, now if you have to look at its count, so how many nodes do we have here? 2 and 0. What's the max? We have 1 and 0, one node and 0. What is the max? 1. So it returned back 1 here. Okay. Now 1 is returned here. We have 0. Now 1 and 0, what is the value? It is again 1 is the max. So 1 is returned to us. I'm counting the nodes here. I'm not counting what is inside the node. I'm not taking the number. I'm counting the number of nodes attached to it. So now here 1. But who is going to count this current node? Whatever we have here, this node also has to be counted, right? So 1 was returned to it. So I am adding plus 1. That is, I'm counting this current node also. So max value, whatever is returned to it, plus the plus 1, so that the current node is also counted. That's what I'm doing here. I'm counting the current node also, so it covers it. 1 plus the max of my left depth and my right depth. Okay, whatever value, number of nodes I have in my left and whatever number of nodes I have in my right, I'm taking the max of it. If I have 3 nodes on my left and 2 nodes on my right, then what is my max? 3 is my max. So 3 is my max plus 1, my current node. So how much did that become? 4 levels. 3 plus 1 will be 4. So in that way, we are going to recursively keep visiting left and right nodes and choosing the max from it and adding plus 1 for my current node where I'm currently standing. And that is going to give me the maximum depth. Now let us declare a tree. Okay, let us declare a tree here. I'm creating a sample input. So I'm giving the root value as my tree node 3. Okay, this is my root value. After that, on my left, root dot left. On my left, I'm giving the tree node 9. On my right, I'm giving the tree node. On my right, I'm giving the tree node 20. Okay, that's on my left side, that is in my right side of my node. On the left of that, I am giving 20. After 20, I am giving tree node 15. And next to that, again, on my left side, I'm giving tree node 7. Okay, so now I have to check the maximum depth of it. So I am telling print max depth. Okay, and root. I am running the root there. So let us draw the tree so that you understand it well, right? So what is my root node I've started off with? I've started off with root node 3, okay? And then I have taken a left node 9. So let me draw a left node 9. After taking left node 9, it says on my right, I have 20 as my node. All right, so 20. And then for this 20, what happens on my left? I am getting 15. I am getting 15. And then what is the other node? I have 7. I have another node 7. So here, if you see what is the maximum depth of my tree, 1 and 1, what is the max? 1. So I have 1 plus I have max returned. So it evaluated my left and right. So left is 1, right is 1. Okay, so between 1 and 1, what's the max? 1 only is the max. So it returned back 1, but it is counting the current node also. So 1 plus 1. So 1 plus 1, 2. So it's returning back 2 here. So 2, 2 plus my current node here. So 2 plus 1 is going to give me 3. So what is the maximum depth here? My maximum depth is 3. So let us check if we are going to get the maximum depth as 3. Maximum depth is 3. The maximum depth of the tree is 3. I hope you understood how we counted it. First, we count the number of nodes on our left and right. We take the max count of it. After that, the current node where we are standing or the current node which we are visiting, we add +1 for that node. And we return it back to the root node of that particular node. And after that, we are going to evaluate the value and add +1 to it and then return back the max again. So that's how we got the maximum depth as 3 or the maximum levels as 3. You can see that clearly here. Okay, this was a small tree, so we could draw it and easily count it. But when we have large trees, we need to rely on our programs only. All right, I hope that you have understood this program also. So here what we analyzed is the maximum depth of a binary tree. Very simple, we just looked at the number of levels in the tree. How many subtrees we have, how can we reach that tree? So that's what we checked. All right, so all of these are using our recursive functions. Okay, let's move on to the next tree. Next question based on the trees. Now the next question is check if a tree satisfies the BST properties. What is BST? BST is nothing but your binary search tree. Okay, BST is nothing but your binary search tree. So we need to confirm if a given tree is a binary search tree or not. So now, what are the conditions to check if a tree is a binary search tree or not? The condition here is whatever value you have for your root node, okay, the value that comes as your left node towards the left hand side of that root, whatever values you get, they all need to be less than your root node value. Okay, so all the values here, since our root node value is 9, all the values that fall on the left side of our root need to be compulsorily, mandatorily less than 9. Okay, so it can be 7, then this 7 can further have on the left hand side 4, and on the right hand side it needs to have a value greater than 7 but less than 9. So I can have an 8 probably. Then again on the left side I need to have a value that is lesser than 4, so I'm giving 1. Then all the values on the right hand side of the root need to be greater than the root. Okay, need to have a value greater than the root. So I'm having 15 here. 15 is greater than 9. Okay, then after that the value here on the left side should be lesser than 15 but greater than 9. So I can have 11. Then after that, again, this side, I can have the value as 14 greater than 9. Sorry, not 14. I can have it as 18 greater than 9 and greater than 15. So you need to have such values. If you look at the left hand side, all the values are less than 9. If you look at the right hand side, all the values are greater than 9. Same thing, if you look at the values on the left hand side, all the values are lesser than 7. If you look at the value on the right hand side, the values are greater than 7 or the root node. So these kind of trees are called as binary search trees. Okay, what are they known as? They are known as binary search trees. So it is very easy to look through such trees. What is the basic idea that we follow? The basic intuition is whenever we have the root node, if we are looking at a binary search tree, then we need to make sure that the value on the left is always less than our root node. It should always be lower than our root node. And the value on the right hand side needs to always be greater than our root node. The value needs to be greater than our root node that is on our right. And on our left, it always needs to be less than the root node. So if this condition is satisfied, then it is known to be a binary search tree or a BST. Okay, so that's what we are going to be doing here. We are going to check the left and the right nodes with respect to your root node. We are going to evaluate your root node's value is lesser than the left side and greater than the right side. When this condition is true, then we are going to declare it as a binary search tree. Okay. So now let me create the tree here. So for the tree, I am going to basically start off with the creation of the class, which is going to have pointer definition, etc. Like what is the structure that I'm going to be utilizing. So let me have a class called as tree node. Okay. Inside this class, I am initializing my function init, and inside this I am putting the self, adding a value, then starting my left pointer as none, then my right pointer as none. Okay, so after this my self dot val, I am going to make it contain the value of my node, then self dot left is going to have the left value, then self dot right is going to have my right value. All right, so we have the values on our left and right, which the pointer is going to contain. Now we are going to start off with a function definition, which is going to check if my given tree is a binary tree or not. Okay, so we are going to check if that is a binary tree or not. So let us start off with that. Definition is validate. We are going to validate if our given tree is a binary tree or not. So what does this given tree contain of? We need to pass the node. Okay, after passing the node to it, we need to pass the low value and the high value, the minimum and the maximum, right? So what can the low value be? Low value, I am declaring it as negative infinity, minus infinity. Now, why are we declaring it as minus infinity? The reason we are taking it as minus infinity is we are not aware of what is the value, least value that we need to compare the node against. So when we are trying to initialize it, we don't have a value. After we have initialized, we are going to get a value, the most minimum value or the most highest value. But to start off with, we don't have any value. So what are we going to start it off with? We will start it with a value called as minus infinity. That's going to be the smallest or the least number that can exist. So low is equal to, I am putting it in the form of float, and I'm going to say minus infinity. All right. So my float value is minus infinity. Then the highest value that can exist is float. I'm going to have highest infinity. All right. So the lowest infinity and the highest infinity. That's going to be my minimum and maximum. Like I told you, we have to have all the values on the left hand side of the tree need to be minimum, that is less than our root node. And on our right hand side, they need to be greater than the root node. But we need to compare it against some value to start off this comparison. So to initialize or start this comparison, we are going to compare it against the smallest number is our minus infinity. The largest number or the maximum number is our infinity. Okay, that's going to be the highest value. So let us create the validation. What is the base case going to be? If there is no value in the node, if not node, then what? Return true. That is, an empty node is valid, right? So whenever we don't have any leaf node there, that means it is a binary search tree because there are no further nodes. So even if it has a single node, it is a binary search tree. So that's why we are returning true. The second condition is if not, okay? If not, the value that we have should always, our root node value should always be between low and high. Why? The root node, I'm writing the root node, you can observe that I am always writing the value between my lowest value and my highest value. So where is my root node present? It is always in the between two values. Between my low value and between my high value is what my root value exists, right? My root value always exists between my low value and my high value. So the same thing I'm going to give it here. If low, what is my low value here? Minus infinity. If my node dot val. What does node dot val contain? My root val. If node dot val is less than minus infinity and greater than high infinity, that is the highest number, that's our positive infinity, then what we are going to say? Return false. Okay, so this is we checking the node value. So what does it say here? It should be lesser. Our low value is less than the node value. Okay, that is the value here is less than our node value, and the value on our high is less than our uh, high value. Then we are returning a false. That means if this case is not justified, it's telling if not, this should be the ideal case for a BST. 9 on the left hand side, we have 7, which is less low. Low is less than your root value 9, and here we have 18, which is greater than your root value 9. Your high is greater than your root value 9. This is the ideal case for a BST. But what are we telling? If not, if this is not the case, then return false. That means return that it is not a valid BST. We are going to return false. Now let us write the true case. So we are returning false here. Then we are going to return again. I am calling my function is validate. Okay, I'm calling my function. Now what do we need to have? The node on my left. Now that was for initialization where we took our infinity value, right? Now whatever node we have on the left, that needs to be less the node on the left. Then we have a root value, which is your current low. Then we have node dot value. That is our current node value. And this is setting up your upper bound is the current node's value. That is your right node is your highest value. Node value is currently your highest, and the root value is your low value, and then you have node dot left. So when this is the case, okay, now let me add and case also. And along with this, okay, there's another function which you're checking is validate. Now in is validate our node dot right, whatever value we have on the right side, and node dot value, that is our root node value. And we have node dot right, we have our root node value and the highest possible value. Now if this condition is also either of this condition, if it turns false, then we will get a false for our binary search tree. So it is mandatory that both our conditions end up as true. That is, our node value on the left needs to be the lowest and the node value on the right needs to be the highest compared to our root node. So when both the cases end up to be true, then we will return true as a binary search tree, true for the binary search tree. But if either of the cases end up to be false, then false and true is going to give us a false only. So that way we are going to return back a false then. So let me create a sample tree. So I am giving a root is equal to, now look at the tree that I'm passing. I'm passing tree node, and in this tree node, the first thing I'm passing is 8. This is my root node. Then I am giving tree node. Now this goes on to my left side of the tree. On the left side of the tree, I am giving a tree node, I'm giving 3. Then on for this number 3, I am going to have a tree node on my tree node below this also. Okay, so below 3, I am having another tree node, and this I'm giving as 1. Below 3, I'm having another node 1. Then after this 1, now again, I am continuing with another tree node. So this is a fresh node that we are starting on the left side of our root node, that is 6. Then we have a right node to it, tree node, and I am going to have on my right side as 6 as my root node. I'm going to have 4 on my right side. And then I am going to have tree node 4, then tree node 7. So on the right hand side, I'm going to get 7. So now left and right both are done. Now let us go back to our tree node of so here, let me look at the brackets. Let me be careful with the brackets. We have 8 as our root node. Then we are having tree node 3. And then we have tree node 1. After that, we are having tree node in which we are having 6. Then we have tree node 4. Here I haven't closed it. And then we have tree node 7. And then after that, after tree node 7, I am going to have a continuity of my right hand side nodes. So here, let me give tree node, and I am utilizing 10 on my right hand side, then none, that means no node on my left, and then again moving down, I have a tree node of 14, and again I have none here, and I have tree node 13, tree node 13. All right, so this is how I have drawn my tree. So how did I draw it? Let me draw it for you here. So I am having, what is my root node? Root node is 8. So I am having root node 8. Okay, after that I have tree node 3 and tree node 1. So on my left hand side, I have tree node 3. And then in the same way, I am having tree node 1. That means on my left hand side, I have tree node 1. All right, this part is done. Now tree node 6 and tree node 4. So here my 3 is going to have tree node 6. Okay, and after this it's telling tree node 4. So tree node 4 on my left side, so tree node 4, and then it's telling tree node 7 on my right side. I am having tree node 7. Okay, after that we are having tree node 10. Coming back to our root node here, now starts our right side, tree node 10. After tree node 10 is done, then we have none, that means nothing on my right. Then comes tree node 14. So here tree node 14, and after that, what is the last node? Tree node 13. So here on the left hand side, tree node 13. Okay, this is the tree that we have drawn utilizing this particular element here. Okay, so now let me continue. Okay, so now let me print if it's a valid tree or not. Valid is valid. I'm calling my function is valid. And what am I passing in that? I am passing my root value. What is the root value? Root value is all my entire binary search tree. So is validate, is validate. Okay, so let's run it. It is true. Why is it true? Let's look at this tree. My value here, root value is 8. Okay, my root value is 8. Let's look at all the values on my left side. Less than 8, 3 is less than 8, 1 is less than 8, 6, 4, 7. All of the values are less than 8. All the values on my right hand side are less than 8, and on my left hand side they are greater than 8. Let us look at the first one, if not node. First node is selected, but we have other node values attached to it. So if not node, that does not hold true. We'll move on to the next statement. If not, low less than node value less than high. What is my node value? 8. 8, is it less than your minus infinity? Yes. Is it greater than your positive infinity? Yes. So it moves on. It moves on. It says if not. So it is false, right? So it is validated, and because of this, we are going to move on to this line here. Here it's going to check if my left node value, that is 3, is less than minus infinity. True, it is less than minus infinity. And is it greater than my value on the right? What is my value on the right? It is 10. It is greater than 10. So that's why, yes, it is true. It is a binary search tree. It keeps moving on and on until we get a perfect answer that yes, it is a perfect match of binary search tree. Then we are going to return that it satisfies all the conditions and it is a binary search tree. All right. So do let me know in case you have any doubts. You all can let me know in the other session. Please make sure that you practice this particular program wherein you have to create a program to identify if a given tree is a binary search tree or not. All right. So moving to the next question that we have here. The next question that we are coming across is construct a binary tree from your pre-order and in-order traversal. So I told you in the beginning of the class that we are going to be utilizing two traversal techniques here, your pre-order technique and your in-order technique. What happens in your pre-order technique? In your pre-order technique, the way your nodes of the tree are visited is first your left node, then your root node, then your right node. Okay. So when we have your in-order technique, we are going to first visit 2, then the root node 1, then the root node 3. So the order of visit is going to be 2, 1, 3. This is going to be your in-order traversal. When it comes to your pre-order traversal, we are first going to visit your root, that is 1, then we are going to visit the left node, that is 2, then your right node, that is 3. This is your pre-order technique or your pre-order traversal technique. Okay, so now we have to construct a binary search tree using these two techniques. All right. So what is the basic intuition for creating this kind of tree or for utilizing it based on this or for utilizing these two traversal techniques, right? So the first thing is we are going to create a class. That class is going to have your pointer definitions or how exactly it is going to work, right? The structure. After that, we are going to build your tree. We are going to define a function that is going to help you build the tree recursively. In the build tree, we are going to give a base condition. After giving the base condition, we are going to pass two lists to it. One list is going to contain your in-order technique, the in-order array. The other list is going to have your pre-order array. Now we need to write the code in such a form that your root is always removed and the same value is looked up in your pre-order also in your in-order. From the pre-order it's removed, and after removing it from the pre-order, the same number is looked up in the in-order so that we can continue designing the tree in that particular order. So that we can construct the tree in that particular order. So first, let us define our class. So we are going to have your class tree node. In this, we are going to define your structure as usual. So this is very important, wherein we give a particular format. So we are initializing that format. We are passing self, and then we are creating a value variable, which is 0. Then the left pointer, I am initializing it to none, but until a value is initialized, it is currently empty. Both left and right. Both the values are empty right now. Okay, after this, self dot val is equal to the value, then self dot left, we are going to have the left value, then self dot right, we are going to have the right value in it. Okay, so this is our IGHT. Okay, this is how your structure of the program will be. Clear? Now, after this, we need to define your function, which is going to help you building the tree, which is going to help you in building the tree. So let us create a function build tree. Okay, we are creating the function build tree. In this, we are going to pass both your techniques, which we are going to be utilizing here. That is your pre-order and also your in order. Okay, so we have both pre-order and in order declared here. In this, if either of our arrays have turned out to be empty, then we are going to return none. So if we have any elements in these arrays, we'll be able to construct the tree. In case there are no arrays in this list, then we'll not be able to create a tree here. So if not pre-order or not in order. Okay. In case you are not a pre-order or you don't want to be associated with anything inside that in order array. So then if not pre-order or not in order, then we return the value as none. All right, so we return the value as none. Now, after this, what is the technique that we are going to have to make sure that we are choosing all of it that falls under in order and all of it that falls under pre-order? How do we construct it with that intention in a very careful manner that both the lists sometime at some point of time end up to be 0 and we move out of that loop? How do we figure that out? So give it a thought, like how exactly we can do it. So we have two traversal techniques here. We need to keep both the techniques in mind and write our program of building the tree. Okay, so here what we are going to do is we are going to initialize your root value. So I have returned the value here, return none. So for that, I am assigning your root value. I'm creating a variable called as root value. And in this, from my pre-order, I am assigning the value that is being popped from my pre-order. That is, I'm removing the very first element from my pre-order and assigning it to a variable called as root value. So what is it? Index value number 0. Whatever we have in index value number 0 is going to get assigned to root value. All right. So after root value is popped, we need to figure out root is equal to tree node, and we are going to have a root value. All right, root value is equal to preorder.pop. We are going to call the preorder function and it's going to remove the very first element. After that, whatever we need in the root is going to come from our root value. Whatever number the root value consists, that's going to be our uh, value for root. After that value is assigned, we have to figure out the index. Now, this was in your pre-order list, right? From your in-order list, what do I need to do? I need to pick up a value that is as same as the value that was popped out. If I popped out 5, my job here in your in-order traversal list is to look for 5 and be along with that value until my program finishes. So root value is tree node root value. Then after that, I'm going to have a root index. Okay. So in root index, we are going to utilize your in order dot index, in order dot index, and we are going to have the root value. So root index is equal to inorder dot index root value. So whatever value we have found as root value, I am going to look for that particular value in our in-order list. And once we have found out, I will check what is the uh, what is the condition of it to proceed ahead with our program. Okay. So we have a root value, which from our pre-order, we popped it out. From our in order, we need to look for that value in our index and search for our index number. So now let us start off with building the tree. Now here we call our function recursively. Okay. This is where we start our recursion. So let's look at the left side of the tree. Root.left. We are going to call our function build tree, and it's going to recursively build the tree. So build tree, preorder. So from preorder, we have already popped a node value here, right? We have already popped the first value that we came across as the node value. For that, we in our inorder list, I am going to look for all the values on the right, right? That's why I'm giving colon. Root index. Okay, so all the values on my right hand side from the root index, I'm going to put it on my left side of the tree. Okay, so we have the root index, all the values look towards the left. Whatever values are there on the left, put it in the left side of my tree. And this is going to happen recursively by utilizing this build tree function. It's going to be called again and again until we do not have any elements left in the pre-order or in the in-order list. Okay, so that is for root left. Now root right. Now on the right hand side, we are going to build the tree. Now on the right hand side of the tree, I'm going to have pre-order. We are looking at the pre-order list. We are not utilizing it. We are only looking at the pre-order list because we have kicked out our root number from there, right? We popped out the root number. That's why we are looking at the pre-order list, but we are not taking anything from there. Here, we are just looking at it, but the actual work is being done from our in-order list. Okay, from the in-order list, whatever root index we considered, we are taking the root index. And here I'm going to add +1 to it. +1 to it. So from the root index, it moved to the next value. +1 it did and moved to the next value. And whatever is falling on our right hand side goes on to become our right side of our entire tree, right? +1 and colon. Okay. Now with this, I will return the root value. So what did I do? I first picked out my in-order list. Picked out my pre-order list. From the pre-order list, whatever is the first number, we popped it out. And when we popped it out, we made it your root node. Okay, now the same root node, whatever we popped out, we are going to look for that value. We assigned it as your root value, and we are going to look for that value of your root node in your in-order list. From the pre-order, we popped it. Now we are looking for the same values index in our in-order list. Okay, in the in-order list, it's searching for that value. Once it finds the value, we want the index value of it to return. This is what we are telling here. Return the root index. In order dot index for the root value which we assigned, which we popped out here, we are taking the root index. So once we have the root index value here, after that's been assigned, now let's look at the values for the root index. Whatever root index value we have, so what falls on the left hand side, if the root index value is here, whatever is coming on the left hand side, because of this colon, we are telling whatever is on the left hand side, this becomes your left tree. Okay, this becomes your left tree. Now, whatever falls on the right side, so root plus 1, root plus 1, it's moved one element here, and whatever falls on my right side becomes the right part of the tree. Okay, that is what this part says. These two lines, that's what it says. And this is being done recursively because we are calling build tree again and again. You can see here, we are calling build tree again and again. So until these two lists become empty. Okay, we have pre-order and in-order list. So that's what we are saying. If not pre-order or not in order, then return none. That is, we are going to make sure that once they become empty, then we are going to return none and stop building the tree. Or else until then, we are going to recursively keep building the tree. Okay, so now let us declare an input here. Okay, so reorder is equal to, here I am declaring the node 3, 9, 2.3, 15, 7. Then in order is 9, 3, 15, 27. Now what happens here? It starts off with my root value. First, it looks into my pre-order list. What is my pre-order list? 3, 9, 20, 15, 17, right? The first element, it popped it. So what was the first element? With 0 index, it's popping it. That is, it's popping 3. Now, what is my root here? Root is 3. Right? So my root value becomes my root. So 3 is my root now. After 3 is my root, now it is asking me to search this root value, which is 3. I have to search for its index in the in order. So what is the index value here? 0, 1. What is the index value? It's 1. So 1. Now in order, whatever we have on the root index, left side of the root index becomes the left part of my tree. So what is there on my left part next to 3? It is only 9. So what is my value on the left side of my tree? It is 9. That's it. Now my list is here empty. No more elements here. Again, it goes back and it pops out the next element. What is the next element? It is 9. It is going to look for my index value here. Index value is 0. This is the right side of the tree. Then my build tree works on the right side. It happens so on and so forth repeatedly until my pre-order and my in-order becomes empty. Once it becomes empty, it stops building the tree. So root is equal to build tree. Now in this, we are going to run both the lists, pre-order and in. Now let us print the root value. The root. Now root value. So when we are printing the root val, mm, root. Okay, here what I've done is I have given variable names are different. So I have root val, and here also I'm giving root val, and here also I'll give it as a root val. Okay, I've given the same names now. Let's run it. root underscore val. Okay. Now build tree, preorder and inorder. Now, if not preorder or not in order, then we are going to return null. Then root val is equal to preorder dot pop. We are popping the very first element. Then root is equal to tree node. From that root val we are picking out. Then root index. From that we are picking out the root val for that index. Then we are using your root left and root right, that is recursively building the tree. Now here we are going to print a root dot val. So let me just stop, interrupt my execution and restart the session and run it. So here I've assigned your value as 0, then left as none, right as none, then self val is equal to val, self dot left is left, self dot right is right. Then I've defined the build. Then if not preorder or in order, we are returning null. Okay, here the if, sorry, my indentation ended up being wrong. I didn't note it. All right, so what did we get? What is our root value? The very first element that it popped out 3. So that's why it's returning the root value to be 3. So this is how we computed or constructed your binary tree by utilizing your preorder and inorder traversal. Now let's look at the lowest common ancestor of binary search tree. What do you mean by lowest common ancestor? Lowest common ancestor means as your tree keeps progressing, at some level, you need to figure out when it has 2 nodes, for both the nodes, the common ancestors that you'll have, that needs to be the least compared to both the values of the node. Okay. So I might give 2 nodes from the tree. Randomly, I might pick out 2 nodes. Now, whatever is that common ancestor for those 2 nodes, which are lesser than my node values, that becomes my least common ancestor. Okay, that is the definition of the least common ancestor in a BST. Whatever node pair we are going to give, for that, whatever is the interconnecting node, the smallest interconnecting node, that becomes the least common ancestor. Okay. So now we'll be defining the class that is tree node. In this, we will define our function, initializing it. We will use the self, then value, we are starting it to 0, then right is equal to none, then left is equal to none. Okay, once this is done, then we have self dot val, then self dot right, self dot left is equal to left. Okay, now we have declared the structure. After declaring the structure, now let's start with the program where we can define the function of it. So let's define a function to figure out the lowest common ancestor. So we have the root, then we have the left node and the right node. Now it can be two nodes, right? It can be randomly two nodes from the tree. Along with the root, we are passing two nodes. So P and Q are two nodes from the tree, some two nodes. For those two nodes, we are trying to figure out the ancestor, common ancestor, and that too, it needs to be the lowest. So now here we are checking for three cases. So what are the three cases that we are checking for? The first is our root value needs to be lesser than the node on the left, that is the P, and node on the right, that is the Q. Case one, then we will return true, okay? And we will move left. Else, we are going to check if our node value is greater, our root value is greater than P, but lesser than Q. Then what? We are going to move right. Or else we are going to say we found the least common ancestor. So while root, then if P dot val is less than your root value, okay, and Q dot val, whatever is the Q value, is also less than the root value. If both of them are less than the root values, then we will say root is equal to, we are moving left. We are going to look for it if there is any value that is smaller than this, right? So root left. Or else, what is our second case? Elif, if our P value, whatever is the value, node value that's been given to us, is greater than our root value, and also Q value is greater than our root value. Okay, if they are both are greater, then what do we have? Root is equal to root dot right. We are going to move towards the right. Now, else we are going to return, else we are going to return the root. That is, we found the ICA or the lowest common ancestor. Now let me give the tree here. So root is equal to tree node. I'm going to declare the tree again. So I will give 8, comma, tree node. And here, let me do one thing. Let me just copy the earlier tree node, right? So let me copy this and paste it here. So what happened? Okay. I pasted the tree node. Now let me give P is equal to, I'm giving node, tree node 1. Q is equal to tree node 4. And then let's print lowest common ancestor. And in this, what are we passing? We are going to pass the root, then we are going to pass the P value, then the Q value, and for all of this, we are returning the values. Okay. Okay, class tree node, and in this class tree node I've initialized the self, then value as 0, then right and left as none, then self dot val right left. Okay, then we are defining the lowest common ancestor, and we have root and pq while we have a root. So if our case is here else root, and then we are defining your root here. Lowest common ancestor. Okay. Let me again stop the execution and rerun it. Let me just rerun this and let's check. I'm rerunning it, and here we are getting the least common ancestor as 3. And what is the tree here that we have? What does the tree look like? We have 8 as the root node. After root node, we are looking at 3. Then we have a root node 1. Then this 3 has 1. Then after that, we are having 6 and 4. Then we have 6. Then after that, we have 4 and 7. 4. Then we have 7. So 4 and 7. Then we have for 8, we have 10. And then what is the next tree? We have none, then 14 and 13. So here we have 14, and then we have 13. This is how our tree looks like. Okay, 14 and 13. Now, what are they telling? We need to figure out the least common ancestor for 1 and 4. That is for this and this. Now, 1 and 4. For this, the ancestor is 6, but it's not the ancestor for 1. So before that, what's the ancestor? It is 3. So 1 and 4, 3 is less than both 1 and 4. So this is the least common ancestor. That is what it's returning. It's returning the value as 3. So this is how you figure out the least common ancestor. I hope that you have understood this program as well. So let us stop the session here. So if you all have any doubts, do let me know in the next session. I hope that you have understood all of these topics, the traversal techniques and the binary search tree. So in case there are any doubts, any questions, please do make sure that you let me know in the next session. I hope that all of y'all would be able to understand today's session. Thank you for attending the session. So let's meet up again for our next session. That is on Saturday. Thank you. Have a great day ahead. Bye-bye.